Okay, Kurt, why don't we get started? So, thank you all for joining us. We are starting the NRAP Webinar series again after a brief pause. My name is Rajesh Pawar. For those of you who don't know me, I'm at Los Alamos National Lab, and Bob Dillmore could not make the meeting today because of a conflict. So I'm acting as a host on his behalf and representing the NRAP technical leadership team. And so we have Kurt Goldenberg today to give us a talk. Kurt is a senior scientist at LBL, Lawrence Berkeley National Lab, and has been working in the CO2 storage area for over 20 years. He has been also working has worked on a few well blowout related incidences, including the Macondo well and also the Aliso Canyon well. And so he basically has been using that experience to look at what are the risks and associated with CO2 blowouts and modeling that particular scenario. So his talk today is going to focus on that, and it's titled Modeling of Offshore CO2 Blowouts for Risk Assessment. So, Kurt, take it away.
Okay, thank you very much, Raj. If I could ask everybody to mute, I'd appreciate it. And the second thing is, Rajesh, I think when I go full screen here, I can't see the chat anymore, but maybe you could monitor the chat, and
yes,
people can start asking questions as I go, and then we can answer them after I finish.
Sounds good.
Okay, so as Rajesh said, I'm going to talk here about the modeling of offshore CO2 blowouts. It can be from a well or from a pipeline in the context of risk assessment. And I'll do this according to this outline that you see here. This is all work for the GOMCAR, Gulf of Mexico Carbon Sequestration Project that's run by the Texas Bureau of Economic Geology.
Hey, Kurt, sorry.
Yep.
Are you in the presentation mode? And you're still on the...
Yeah, it says I'm sharing my screen. You're not seeing a slideshow?
No, now we are, and then it's still on. Okay, there you go. Now it's the acknowledgements slide. So.
What? You're seeing a screen that has several titles around it with my cursor moving?
Yeah, with the title.
Yeah, that's the correct slide. That's the correct slide. Yeah. Okay, so this is the outline basically, Raj. So I'm going to start with an introduction to this project. Then I'll talk about some analogs that are very relevant. These are natural gas blowouts offshore. I'll talk about the differences between offshore and onshore blowouts. And the focus of this talk is going to... Okay, can someone please mute? I'm hearing an echo. The focus of this talk will be on the atmospheric dispersion part of this problem, and this is where the NRAP multi-source leakage ROM, or MSLR, is going to come in. And then I'll go over the overall methods and come around to the conclusion. Okay, so the GOMCAR project is motivating this work. It's looking at the near offshore Texas Gulf Coast, a little bit of Louisiana. Shown over here in this figure is a map that's showing this porosity thickness product. So where you're seeing these sediments extending offshore, showing up in white and brown. This is a very high capacity, good potential for CO2 storage area. There's this 9-mile state water boundary shown in red here. And so they're looking in the project at the very near shore opportunities and some depleted oil reservoirs. And so this area is really promising. It's a very well-studied geologic basin. It's got a high concentration of industrial emission sources along the coast. Again, got a very good sink. There's a lot of capture and transportation facilities already in place and more potentially in the future. And then there's a possibility of EOR to offset some costs. As I said, this project is run by the Texas Bureau of Economic Geology by Suho Vorka, Meckel, and Ramon Trevino. So, as I said, a very well-studied basin. And what comes along with that, as we all know, is the hazard of leakage through wells. Okay, so a bunch of wells are plotted here on this map. So we have good characterization, we've got good infrastructure, we've got good sources, but we've got this hazard of leakage through wells. So zooming in a little bit more, you can see here a little part of the Texas Gulf Coast, this 9-mile boundary. If someone could mute, I'm still hearing a little bit of feedback. This is actually this is the 6-mile, forget about that boundary. This here is the 9-mile boundary out here, and the 24L and the 10L are two oil fields that are of interest to the project. And so they're shown here, 10L and 24L. You can see these other oil fields in the area. I've just plotted this slightly differently here. It's the same coastline, same orientation, just to show you the bathymetry. So the 10L is in about 30 feet of water, and the 24L is in about 36 feet of water. Okay, so these are very shallow, very near shore parts of the Texas Gulf Coast. So offshore natural gas blowouts are a very useful analog to the potential for CO2 blowouts. So shown here is one from the North Sea. Here's a platform for scale, and there's clearly something coming up out of the water here. This is natural gas. There's another very dramatic one here, 1993, off the coast of Vietnam. You can see this big disrupted area of the sea. This is all caused by a methane blowout coming up from below. So let's look at that in a little more detail. I'm going to play a video here. Don't worry about the sound. There's no narration or anything, but I just want to show you what these things look like. So I'll skip around a little bit in this, but this is 1993 in Vietnam. These are shots from a helicopter. Let me skip out here to, about 125 seconds or so. Show you, again, looking from above the platform, and then this very turbulent water. So there's this enormous outrush of methane, unignited, coming up out of the sea here, causing a big disruption to the sea surface. You can imagine there's a big plume here. So methane is much lighter than air, so it would tend to just move upwards in the atmosphere, mix. This is a side view showing this methane coming out, disrupting the sea surface, so clearly a big hazard for ships and boats, etc. Let's go out here to just a faraway view, looking at the big picture there, and then again, the dynamics of this. Okay, so imagine now, going back to the PowerPoint, the situation for CO2 could be somewhat analogous, but again, as I mentioned, methane is a light gas relative to air, so it tends to move upwards. In the case of a CO2 blowout, you have a dense gas relative to air coming out. So we have many examples of this from the onshore environment. Famous one I'm sure many of you know about is the Sheep Mountain Dome, because there's a nice paper written about it and the attempts to kill that blowout. It took 17 days to kill, but it's a very nice paper if you get a chance to look at it. Much more recently, this is just a photograph from a newspaper story in 2015. You can see there's a blowout going on here below this rig, and you see kind of this white fog. This would be condensing water in the atmosphere, condensing due to the cold CO2 coming up, probably cooling by expansion. And again, this tendency for things to kind of flow along the ground rather than mix upward is really a big part of the CO2 risk for the onshore situation. Here's a really famous one also in Hungary. They had a lot of extreme expansion cooling, producing dry ice, and ended up doing a really elaborate feat of trying to heat this with a mobile jet engine, actually, so they could get in there and try to staunch the flow. But these are all onshore examples. But typically, if we're moving into the offshore with carbon sequestration, we have to expect that that could happen. I just want to show another example of a pipeline onshore, and this was just a year ago right now, not very well known, but this was the Denbury pipeline from Jackson Dome, suffered a rupture, and you can see again the effects of the expansion cooling. We get a lot of dry ice, and if you're wondering about the scale of this photo, let me zoom out just a little bit. This is a big pipeline. Here's some people here. So we have these experiences in the onshore, and that's usually what we've been thinking of in NRAP and developing NRAP tools, etc. But what I'll be showing here is that we can apply some of these to the offshore situation, but we need to appreciate some of the differences. So the main differences between an offshore and an onshore CO2 well blowout will occur after the fluid leaves the seabed. Okay, the geology is pretty much the same onshore and offshore, but once the CO2 leaves the seabed and moves into the water column, hugely different from the situation onshore. So specifically, the CO2 will have a lot more resistance to flow and flowing through the water as opposed to the air. It'll have a really strong positive buoyancy. It'll tend to rise upwards as opposed to on land. It's a dense gas. There's a vast source of heat in the sea to compensate for decompression cooling and very efficient heat transfer also. And then we have almost an infinite sink for CO2 dissolution also. Okay, so these are the differences in the offshore case versus the onshore that we're somewhat familiar with. Okay, so moving from analogs and the offshore-onshore, as I said, I'm going to focus a lot of this talk on the atmospheric dispersion piece. So let's dive into this. So I'm going to talk now about the dispersion of a dense gas like CO2. So first of all, just to get your bearings, density on this axis versus gas mixtures from pure CO2 to pure air. Just look at these curves for now. Air has a density of about 1.8 kilograms per cubic meter at atmospheric conditions, whereas CO2, air has a density of 1.2, CO2 a density of 1.8. Okay, so 1.2 to 1.8. And generally speaking, when we talk about a dense gas, it tends to be the case that it doesn't mix as freely. Methane, for example, has a density of 0.68 kilograms per cubic meter at these pressures and temperatures. So methane will rise up and mix very effectively and kind of get out of our space and not be a big problem for us. But dense gases we tend to worry about. But there's some wrinkles, as I'll describe in this talk, to that sort of understanding. So specifically, a density contrast does not always inhibit mixing. So I want you to consider a thought experiment here. We have a container of gas on a flat surface at ambient pressure and temperature. Okay, so there's some air, and then I've got this container of gas. Now, if I can magically at T equals 0 just remove the walls of the container of this gas, we just remove the walls and observe what happens. Well, if I don't have any wind, a purely passive gas, like another air with maybe some different isotopic composition, will really, in theory, mix only by diffusion. Okay, there's no advection, there's no convection, there's no turbulence. It'll just sort of disperse by diffusion. If I have a dense gas in this box and I remove the walls, it will flow on its own. And the very act of it flowing causes the tendency to mix. It increases the area, and there may be some turbulence and some eddies and whatnot. So a dense gas alone doesn't mean that it will necessarily mix less. So a lot of the work in this field started in the late 70s and the 80s as the desire to build liquefied natural gas terminals arose. And this community and the industry did a lot of field experiments of dense gas dispersion to understand how a leak or a disaster might unfold for liquefied natural gas. Now, liquefied natural gas itself would be lighter than air, but it's very, very cold. And so the cold temperature makes it a dense gas relative to air. So these are some of the experiments, and there's just a whole slew of papers on this. It's really fascinating how much work was done on this. What you're seeing here is a continuous LNG spill done in the field. The scale here, that's about 125 meters. There's a 4.8 meter per second wind. You can always multiply these meters per second by about 2.2 to get miles per hour. So we're looking here at LNG being emitted constantly in a wind field. These various things you see floating around here, these are all sensors and instruments that they use to measure composition, concentration, and wind speed, etc. So this is just a snapshot of one of these cases. Here's another one. It looks like it's in the same place. This is of propane. Now, propane is C3H8, so it happens to have the same molecular weight, 44 grams per mole, as CO2. But again, a very cryogenic situation here, so it's cold and it's dense. And you can see it spreading out in a much lighter wind. And so we don't have a predominant stream due to the wind. It's just spreading out a very, very dense gas in sort of a circular pattern. So anyway, these experiments went on, beautiful collection of papers, a lot of work was done. And what stands out is the work of Britter and McQuaid for me. And they gathered, a lot of the data from these field trials, they called them, and with their knowledge of dimensional analysis and fluid mechanics, were able to kind of group appropriate terms and figure out correlations that would fit the experimental results that they observed. And so this is an example of one of these correlations. We've got this x2 over this quantity to the 1/2 equals some function of this quantity to the 1/5. And it's like, what? What are these quantities? Well, they have some pretty good rationalization, and I'll just demonstrate one here. If I have this reference a wind velocity in the background blowing in this direction, and I have a flow rate coming out of a leak at 30 kilograms per second of CO2, I can make a prediction of how this initial concentration C0 will change downstream and become Cm at some different x. And it's some sort of a function of these variables. And it just happens when you plug in the numbers that at 200 meters, this ratio of Cm to C0 is about 0.05. So I reduce this concentration by a factor of 20 after 200 meters in this wind field. And this is all empirical, but by virtue of these correlations, one can then make predictions about the dispersion of dense gases. Overall, these empirical results all suggested that atmospheric dispersion is pretty effective at diluting dense gases, but you always have to remember calm conditions or topographic effects are not really included in these kinds of correlations, and they may motivate you to use more sophisticated numerical modeling approaches. So Britter and McQuaid, again, put together all their results in a series of nomographs. And so these are some very simple figures in which the data and their correlations are essentially encoded. And so you can see this familiar now looking quantity on this x-axis and this other quantity on the y-axis, and then sort of a third dimension plotted here of the Cm over C0, and it says full-scale data region. So they had data in this sort of region as plotted as a function of these different variables, and they had observed these dilution factors for the plumes that they experimented with. And so this is kind of a elaboration of the result I showed you on the previous slide, and that is, for this Q0 flow rate of 30 kilograms per second, translating that into a volumetric flow rate with this reference velocity, I can then compute this term Q0 over U ref to the 1/2. I get 2.9 meters. So that's the term on that x-axis. So I can understand what, x would be, which would be this dimensionless, the y-axis value would be that dimensionless value of 70. And I could do the same thing down here, looking at this reduced gravity term for CO2, creating this quantity that's on that axis, and I get a 1.7 dimensionless. So I come out here in this plot. This is 10 to the 0 or 1. This is 2. 1.7 is somewhere here, and my other value on the x-axis is 70, so I'm somewhere in here. So you can see I get this value of 0.05 for that particular dilution factor for 200 meters. So that's how these nomographs are used. And so very conveniently for NRAP, Yingxi and I worked on this to develop the multi-source leakage ROM. And what Yingxi did was to basically encode the nomograph into Fortran, and that got made into the MSLR. Now, she and I did a little more because you notice it's a multiple source, so we put in a little bit of logic so that we could handle multiple sources rather than just one source. But still, that what this is, here's just some screenshot from the actual NRAP tool where you put in some of your properties of the system, the wind speed being a very important one, the concentrations that you're interested in, and some targets and things downstream. And you can then click run, and this thing runs. And as you can tell, because it's just the encoded nomograph, it's instantaneous. There's really no serious computation that's done. So it's very, very fast. And does this thing work? I mean, what are these nomographs? So we also, in this paper, you'll see a description of our work in comparing the simple Britter and McQuaid nomograph approach to Panache, which is a CFD, computational fluid dynamics code. So we mocked up this problem where we had two sources, we have a wind, and we compared the MSLR, or the Britter and McQuaid approach, to the Panache approach, and you can see the dilution is pretty much matching quite well. So the MSLR seems to be a pretty good representation of very simplistic atmospheric dispersion, but of even a dense gas. That's really the point. These are for dense gases. Okay, so let me just clarify one thing. The MSLR doesn't really use a wind direction. Instead, it assumes the wind could be in any direction at all times, okay? So it's kind of like a one-dimensional model. We don't care about the wind. Think of it as always being accurate, as if there were a wind in any direction. And it's not that there's wind in all directions at the same time, but in any direction at any time there's a wind. And so we just are looking typically for a downwind dispersion length or a downwind safety length. How far do I have to be away from this, regardless of wind direction, to be at a concentration that I'm comfortable with? That's what the MSLR is finding. Okay, so that's the atmospheric dispersion MSLR piece. Let me go now getting into the bigger picture of the problem that we're looking at for this offshore system, and that is sketched here. We have a reservoir in the deep subsurface below the seabed, connected to the seabed by a well that's connected to a CO2 source by a pipeline. This is all below a water column, and above that is the atmosphere. So in this project, what I do is model this entire system, kind of these four different regions of the subsurface, the well, the water column, and the atmosphere. So I'm going to go really quickly. I've talked about this before and have a paper on it, so I'm going to go very quickly on these methods of T2 well and TAMA, because I think many of you know them anyway. T2 well couples the reservoir with the well. TAMOC looks at the CO2 that's leaving from the wellhead or nearby in the pipeline into the water column. So that's sketched here. By the way, some numbers from the T2 well result are shown here too. So from a 2-inch hole, we have basically 1 million tons per year capable of escaping in a jet, very high velocity, with some decompression cooling going on, but it comes into the water column and causes all kinds of bubbles and slows down and whatnot. So this is TAMOC. It does an integral modeling approach of a buoyant CO2 bubble plume. And so in the integral model, this plume is divided up into a whole bunch of pieces, and we have vertical velocity in and vertical velocity out. The all-important entrainment velocity. As the CO2 bubbles are rising, it entrains more seawater. And then entrainment velocity is usually about 1/10 of the vertical rise velocity. So TAMOC is the Texas A&M oil spill calculator or outfall calculator, and it models a whole lot of different things as you see here by this interval approach, not a CFD approach. And one of the most important aspects of it, or most important inputs, is the bubble size distribution. And so that's something you calculate a priori based on the speed of the input, the source. And so this is the workflow that we use to give the bubble size distribution to TAMOC. It assumes this Rossen-Randular distribution, and it's basically based on density and velocity of the in the length scale of fluid that's coming into the source. And so the bottom line here, this is the distribution of bubbles that come out of that hole in the pipeline, and the mean size is about 0.5 millimeter. Okay, these are very small bubbles because we have such a vigorous input of CO2. So again, quickly on TAMOC, we have some initial particle size distribution. That's what I've just shown you. They are CO2 bubbles. They come in at a certain rate. And from there, I used what's called the bent plume model. So this could have a transverse water column velocity, like a current in the sea if you wanted, and I put in just a nominal one. So I used the bent plume model. And then at every time step, there's a discrete bubble model that's looking at the loss of CO2 from the bubble to the water, looking at the temperature, looking at the salinity if you have changes in salinity. And here's just a little bit of the details of all the methods that are in the TAMOC. It's basically kind of like a bubble population model, and then each bubble class is modeled by this discrete bubble model. There's some ordinary differential equations solved. It's in Python. There's some Fortran underneath. But it is also a very fast solution that takes like 2 minutes to solve the problems that I was looking at. So let me show you the results then of this mechanistic modeling. I'm going to show some end members. This is the 10-meter deep case, and this is a 50-meter deep case, and I did in between here too. Again, I've got T2 well that's feeding CO2 up to this point, and this is a result in the 50-meter water column, 35 kilograms per second, 13 degrees. Note for the 10-meter deep, it's a little bit higher flow rate, a little bit higher velocity, and a little bit colder. Okay, the reason is there's less back pressure, less hydrostatic pressure in that 10-meter water column than in this 50-meter one. But let's look at some results now. So for T2 well, this is the mass flow rate coming out of that hole in the pipe near the well versus log time. And we've got results that are dashed for the 10-meter water column case, solid curves for the 50-meter water column case. So there's some early transient stuff that goes on, but I just want to focus your attention on these final results, that there's CO2 coming out of that hole that's very similar for the 50-meter and the 10-meter case. Okay, the 10 and 50-meter deep water column doesn't make that much difference to this high-pressure CO2 coming out of the hole. Now, on the temperature side, there's a little more difference between the two, again, because of the decompression cooling effect. So there's a little bit more decompression cooling. It's colder as the CO2 exits for the 10-meter deep water column case. So these are the inputs then to TAMOC, and these two figures over here, the results I want to discuss and focus your attention on. So let's look first at this lower figure. We've got the CO2 emitted at the sea surface as a function of water column height. So again, I did the 50, 40, 30, 20, and 10-meter deep water column cases. And what this is showing is that for a 10-meter water column height, just about all of the CO2 that exits out of this hole in the pipe is calculated by T2 well, also exits out the sea surface. Okay, there's very little absorption or dissolution of the CO2 in this 10-meter deep water column. But as the water column gets deeper, more and more of that CO2 is being dissolved or absorbed by the water column till you get to 50-meter water column, and just about all of the CO2 that was emitted here gets absorbed. Okay, so here's a plot also as a function of the 5 different cases, and this is now the time from the leak point to the surface. So remember that this water column is capable of really slowing down this flow, slowing down the CO2 transport as bubbles are finding resistance from the water. But in the 10-meter case, again, it takes less than a second for the CO2 to get out the top. Okay, it basically blasts out the top. For 20 meters, it's a little slower. When we get to the 50-meter case, it takes 5 seconds for CO2 that's coming out of that pipe to get out the surface of the sea. Okay, so we've got the timing, and we've got this absorption effect, this attenuation effect going on. So let's talk about now what I said I was going to talk about, which is the atmospheric dispersion part. Britter and McQuaid, looking at the left, developed a criterion for whether a flow would be a dense gas flow or an ambient gas flow. You could also call that active versus passive. So if it's active, that means that the gas itself can drive itself like down a topographic slope. Whereas if it's passive, it's just basically the same density as air, and it's reliant on external currents to drive itself. And so there's a criterion that Britter and McQuaid put together, and it's actually a function to some degree of the length scale of the source. And so I've plotted all the curves here for different length scales of the source. And this is a function most strongly of the mass flux of the leak, let's call it, out of the ground in this case, and the wind velocity. So as I have higher and higher wind velocities, I'm able to mix the leaking gas more and more, so I can handle higher and higher fluxes. And as it gets calmer and calmer, even a pretty small CO2 flux can be a dense gas flow. So let's look at what we have for the case I've just shown you. For the different water column cases, I've got these different fluxes at the sea surface. So for the 10-meter case, I've got a flux of 4 kilograms per cubic meter per second. And so plotted on this graph, you can see I'm definitely going to be in an active sort of flow regime. Whereas when I get down to these deeper cases where I've got 0.03 for my flux, depending on the wind speed, I may or may not be, and depending on the length scale, I may or may not have a dense gas dispersion case. Okay, so that's one result of this analysis so far, that I'm often going to be in the dense gas dispersion case over the sea surface. So here's the main result now of the MSLR. Okay, so this is the NRAP multi-source leakage ROM. These results provide downstream distance for the CO2 concentration to reach 0.05 or 1/20th of its original concentration. So once again, I'm making this plot as a function of the 5 different cases for water column height, and this is the downstream dispersion length, or how far does it have to travel before it reduces by a factor of 20. So these results are kind of interesting. Let's look at some. This is as a function now of wind speed, the different color curves here. So let's look first, a very slow wind, again multiply by 2.2 if you want to get miles per hour. A 0.5 meter per second wind speed has a downstream dispersion length of this value for the 10-meter case, and this value for the 30-meter case. Now as the wind gets a little bit stronger, like 1 meter per second and 2 meters per second, those downstream distances actually increase. Okay, so you have to go farther away to be safe. But then, as the wind speed gets up to 10 meters per second, those downstream distances are smaller. Okay, so there's a reversal here that is along the lines of what I've been describing in dribs and drabs throughout this talk, and that is when you don't have much wind, nothing moves very much. And then when you have wind, it moves. But when you have wind, it moves and mixes. Okay, so there's sort of a trade-off. There's sort of this nonlinearity here where you extend the region of hazard, but then you reduce it as soon as the wind gets up to a certain height. And that's kind of seen in the nomograph, I think, by the curviness of it. There's some times there when this nonlinearity of dense gas dispersion shows up. And again, this is all coming from the MSLR applied to the fluxes that we saw, that I calculated in the output from TAMOC. Oh, I guess I'm just saying it here. So just to illustrate that more, there's a trade-off between wind transporting gas and wind dispersing and diluting the gas. So if there's no wind, it doesn't move, and the safety distance is short because nothing's moved. If there's wind, the gas moves, but at the same time it disperses. So you've got a nonlinearity effect. So just to conclude, what I've presented is results from a loose coupling of 3 models of T2 well for the subsurface, and then the well, and then when it gets emitted into the water column, I use TAMOC, and then when it comes out of the sea surface, I use the NRAP MSLR. And the preliminary results here are that the bubble size is about median bubble size is 0.5 millimeters, which is quite small. 99% of the CO2 gets dissolved in the water column if it's 50 meters or so, and if it's deeper, even more would. On the other hand, completely contrasting, if it's only 10 meters of water column, 94% of the CO2 would be emitted at the sea surface. And that's kind of, I think, what we're seeing in some of those methane cases, the methane solubility being much smaller in seawater than CO2 solubility. And then on the downstream dispersion distance, so once we're above the sea surface for the risk and safety of people above ground, I really want to be a few hundred meters away from that source in order, and even if there's a wind of about 10 miles per hour, I want to be that far away in order to be safe from inhaling high concentration CO2. Now, what's high concentration? I used 0.05 as this number, and it happens that if you read the NIOSH, even 4% is considered immediately dangerous to life and health. But I'll just point out that every time we exhale, we're exhaling air out of our mouths of about 4%. So this might be very dangerous, but it would be at a continuous sort of exposure. And just want to acknowledge the Goldenberg project for this work, and I'm available, and I have more slides in case the questions get into some more technical issues. Okay, thanks a lot.
Thank you, Kurt. That was an excellent talk. I have one question from Bill, and then I have a question myself. So Bill Carey asks, at what depth is liquid CO2 denser than seawater and therefore won't migrate rapidly to the sea surface? I think you kind of addressed that, but go ahead. So I don't know exactly the number. In these cases, we're very shallow in the sea, and we are, let's see, our emitted CO2 you saw was coming out at about 8 and 13, between 8 and 13 degrees C, so very cool. At that point, it's coming out at very high pressure into the relatively lower pressure water column. So, I mean, we don't really have a buoyancy-driven flow at that point. It's very much a jet-driven flow. So, I think, I don't know exactly. I'd have to look at that. And then it just wasn't really relevant in this problem. It would be relevant for, let me just click on this one, for this figure, which I just grabbed from somebody, where you have just very incipient seepage coming out that's just barely forming bubbles. That's where I think you could compare and you would need to look at the buoyancy and the density of the liquid CO2 versus seawater. But in this case I've looked at, it's totally advection dominated. Okay. Then Abdullah has a question. How is the dissolution of CO2 bubbles taken into account? Is it equilibrium or kinetic expression?
Equilibrium. So let me take advantage of this opportunity to, since I sense there aren't, let's see. I'm going to go to some other slides. Sensing there are not a lot of questions, I want to show something that I think will help Abdullah and maybe some of the others of you. When I first looked at this, I was really disbelieving at how effectively the water column absorbed the CO2. And so there were some times when I just was really struggling with ways to rationalize this. So Abdullah, what I'm going to show here is a simple analysis, an order of magnitude sense on how an individual bubble dissolves. And so this is a single bubble here. It's got this surface area. It's got this volume and this mass inside of it. And there's just this mass transfer equation that's solved in TAMOC for each bubble of this characteristic that's looking at the rate of change of mass with respect to time. And it's controlled by this concentration that's just outside the bubble in the seawater itself, and then the ambient seawater concentration. And so what I'm going to do here is look in an order of magnitude sense, kind of change this equation around and look at what the time scale is to dissolve a given mass in that bubble. And so in the text here, I'm not sure I'll go through everything, but I just make a bunch of very approximate, never, always conservative, let's say, assumptions about the properties for this bubble. And one of the key things to keep in mind is this number right here, that the solubility of CO2 in seawater is about 2.62 kilograms of CO2 per cubic meter. It's just really, really high, and it's even higher, at higher pressures. And so there's just a lot of solubility. And if I just plug in the terms into this equation, I find the time to dissolve that 0.5 millimeter bubble is 1.14 seconds. And if you recall, the Plume needed 5 seconds to reach the surface in that 50-meter case. And so there's plenty of time over 5 seconds to dissolve the medium-sized bubble. And so this was one of the ways that satisfied me that this result seemed reasonable. Now let me show you another one. Another one is to look at what's the rate of seawater entrainment that I would need to fully dissolve the CO2 blowout flow. So remember this integral model. Here's some of the geometry sketched of an integral model. And remember I said this entrainment velocity was really important as this bubble plume is moving up. And it's about 1/10 the vertical velocity, just a rule of thumb. And so I went through and did the same kind of order of magnitude thing, looking at the solubility, looking at my flow rate, my mass flow rate of CO2, and the solubility, and to get how much seawater I would need to entrain. Okay, I need 18 cubic meters per second to entrain that. And if I look at the surface area of that cone in the 50-meter case, and I look at the vertical velocity as being about 10 meters per second, and knowing that entrainment is about 0.1 of the vertical velocity, I find that I'm entraining, or I could be entraining about 66 times more water than would be needed to dissolve that medium-sized bubble. And so again, on this basis, I'm just entraining all this fresh, so to speak, seawater capable of dissolving bubbles. So this was another thing that, for me, helped me believe the TAMOC results. Now, finally, then I'll go back to you, Raj, if there's another question or two. There's a lot of corroborating work, it turns out. So all very recent stuff coming out. Jonas Gross, by the way, helped me in using TAMOC, and he looks at this Panarea natural seep in Italy. So these are beautiful champagne-type springs of CO2 coming out of the seafloor. And they, too, just observe this very rapid dissolution of these CO2 bubbles, and he simulates that and finds very rational results. Now, Olsen and Skatenay, I was also in contact with. They do CFD on these kinds of problems, and shown here is a contrast between a methane release at 95 kilograms per second and 30 meters of water, and how methane, again, a CFD model, easily makes it to the surface. It's got a very low solubility. CO2, now this is an enormous flow rate, 261 kilograms per second, but their CFD suggests that a lot of it dissolves. Some of it makes it to the surface, but a lot of it actually dissolves in 30 meters. So it turns out it's not outrageous at all for 50 meters of water to be capable of absorbing all of the CO2.
I think that answers Bill's question as well.
Did he have a second question?
Well, he just said, won't the entrained fluid, wait. Okay. Sorry about that. He had a question. Are you saying that dissolved CO2 does not reach the surface? That was tag on Abdullah's question. And then the other question was, but won't the entrained fluid rise to the surface and depressurize and then release the CO2?
That's a good question. Yeah, that's a good one. Some of it should do that. Yeah, very good point. Yeah, the solubility really is a strong function of pressure, not an exsolve. Yeah, I don't believe that's. I'm not sure it's in TAMUC or not. Good question.
So I had a question, Kurt. So the numbers that you use for CO2 release, how comparable they are to the Sheep Mountain blowout? And the reason I'm asking that is, they observed, pretty much ice chunks. I mean, frozen CO2 going out, and so bottom line, the decompression cooling was so much that the CO2 was actually freezing as it was spitting out of the well. I'm assuming, given that you do account for decompression cooling, your flow rate seems to be lower than that.
It's a big difference between seawater and air, I would say. Remember what I said here, that there's just this vast source of heat in the seawater to compensate for decompression cooling, and there's very effective heat transfer provided by water, to that decompressing CO2.
Yeah, so, sorry, go ahead.
Yeah, you saw my temperatures were like 8 degrees C and 13 degrees C. So there is decompression cooling, but the seawater, I believe, is able to heat that, to provide heat, to keep it from getting into these conditions like, dry ice or hydrate type conditions.
Yeah, actually, I was wondering about, whether you are going to observe decompression cooling in the wellbore before it gets to the seawater column.
Oh, you do, for sure. Yeah.
So are you taking into account that effect?
Oh, yeah. Yeah, I mean, just to be totally...
Or how comfortable is your...
Where am I gonna... Okay, this might be a good enough one to show this. You may wonder why we didn't have the leak right at the wellhead. And the reason was we were getting into conditions that we can't handle in the model.
Okay.
And so by offsetting it by, I think this was 10 meters, we're able to have a decompression that is not as big as if it had been emitting right here.
Okay, gotcha.
So, but we do model it, but again, it's hard to model.
Yeah. All right. Any other questions? I think you will be able to unmute yourself and ask question.
Just thanks, Kurt. Very good talk.
Okay. Yeah, you're welcome.
Was that Bill? Yeah. All right. Well, if there are no more questions, you can always follow up with Kurt. I think his email address should be available in case you would like to get additional information about this, and also MSLR and the tool that is available through NRAP. I want to thank you again, Kurt, for this excellent talk. Really, really cool work for sure. And I think we should be good. Thank you all for attending.
Thanks, everyone.